the life, work, and legacy of one of the most brilliant minds in the history of physics, P.W. Anderson, whose contributions have reshaped our understanding of condensed matter physics. So today, first we'll have a talk by Professor G. Bhaskaran and followed by a panel discussion. And today's session will be chaired by Professor S. Ramakrishnan. Welcome and thank you for joining us. And now I invite Professor Kuldeep Kumar Sharma, IAPT Regional Council 23's President, for formally welcome the speakers and guests, and also to introduce chairperson of today's session, Professor S. Ramakrishnan. Over to you, Professor Kuldeep Kumar.
Thank you, ma'am. Good evening, everyone. After the successful deliberations of 2 days proceedings, on the third day of this ongoing 3 days evening webinar on More is Different Legacy of a Nobel Laureate to celebrate the birth centenary of Sir P.W. Anderson, I am pleased to welcome each and everyone present here from the core of my heart. Today, we are privileged to have second expert talk by our esteemed speaker, Professor G. Bhaskaran, on there is room for room temperature superconductivity. And then this 3 days evening webinar will conclude with panel discussion on opportunities for doing small science, focus on condensed matter physics in the era of quantum revolution 2, by a team of eminent researchers and academicians, panelist Professor T.V. Ramakrishnan, Professor G. Bhaskaran, Professor S. Ramakrishnan, Professor Arun Grover, and Professor P.C. Deshmukh. The moderator of this panel discussion session will be Madam Professor K. Dharamveer. The chairperson of today's session is Professor S. Ramakrishnan, sir. On this occasion, I extend my hearty welcome to all our respected speakers and panelists. I would also like to extend my heartfelt welcome to our esteemed IAPT President, Professor P.K. Alwalia, IAPT General Secretary, Madam Professor Rekha Ghorpade, all IAPT members, students, and other dignitaries present here. I hope we all will enjoy listening to the very insightful and enlightening and thought-provoking talks and panel discussions, interactions by our galaxy of outstanding researchers and academicians on the board with us today. Now, let me introduce briefly Professor S. Ramakrishnan, the chairperson of today's session. Professor S. Ramakrishnan is a renowned physicist specializing in low temperature and ultra-low temperature physics. He has had an exceptional career spanning over 40 years, including serving as director of TIFR Mumbai and currently working as a distinguished professor emeritus at IISER Pune. He did his MSc Physics from IIT Madras in the year 1977 to 1979 and joined TIFR for his PhD from 1979 to 1985 to study superconductivity in transition metal compounds. He has published more than 300 research papers in reputed international journals and delivered numerous invited talks at prestigious conferences worldwide, showcasing his expertise in the areas like superconductivity, magnetism, and strongly correlated electron systems. Notably, he discovered superconductivity in bismuth at ultra-low temperature of 0.53 millikelvin, solving a 50-year-old scientific puzzle. Professor Ramakrishnan established India's only laboratory capable of experiments across a vast temperature range from 400 Kelvin to 40 microkelvin. And this includes designing and building advanced setup like adiabatic nuclear demagnetization refrigerator. His contributions have also led to discovery of unique materials and phenomena such as unconventional superconductivity, charge density wave systems, and vortex matter transitions. A dedicated mentor, Professor Ramakrishnan, has trained many students who are now holding leading positions in academia and research globally. He has received several prestigious awards, including Friedrich Wilhelm Wessel Research Award 2001, JSPS Award 2010, and many other awards, including Young Scientist Award. Beyond his research, he has been a part of several international advisory committees and served as Vice President of IUPAP C5 Commission. Currently, as a Chanakya Professor at iHub Quantum Technology, ISER Pune, he is actively contributing to the development of quantum technologies. Thank you, sir. We are honored to have all of you with us. Now, I invite Professor S. Ramakrishnan to please chair the session. Thank you. Jai Hind. Over to S. Ramakrishnan, sir, please.
Thank you. I think we are going to have an interesting talk by Bhaskaran and then followed by a panel discussion. So let me just invite Bhaskaran without wasting any time. Bhaskaran, over to you.
Thank you. I will...
There is a crosstalk. Go ahead.
Oh yeah, do you see my screen?
I can't see your screen.
You don't see it now? My God. I see it. Let me check once again. So I stop your... Do you see it now? Ramki?
No, sir.
No,
It's
not yet.
Zoom is coming.
Oh, Zoom is coming.
Zoom, join a meeting, something like that.
It's not yet coming? Okay, sorry. I don't know what I'm doing. So I stop sharing.
I think,
Stop
yeah.
sharing this and now.
So I will start again.
Yeah.
Start. So select Windows or screen.
Yes, sir, your screen is there. Now you have to select your, it's
Okay.
visible.
Yeah.
Okay, wonderful.
Now.
You see my screen?
Yes, sir.
Okay. Is it there now?
Yes.
Wonderful.
Yeah, it's perfect.
Sorry for the mess once again. And I don't know when I'm going to learn this product. Every time I do it, it happens. But anyway, there is room for always progress. So today my topic is there is room for room temperature superconductivity. I believe in optimism because as somebody said, optimism never hurts. So it's fantastic that we are celebrating this great man on his 100th anniversary. So, and also I want to thank at this point my mentor and Professor Narendra Kumar, who joined the Institute of Science at Bangalore in around September 1970, and I had joined the AIS as a PhD student. So he gave a beautiful course on many-body theory, quantum many-body theory, introducing second quantization and BCS theory and so on. It's so exciting. And also he gave a talk about the work that he and Professor Guide K.P. Sinha had done on possibility of photoinduced superconductor. So my interest in superconductivity started long back in 1970, thanks to people like Kumar and so on. Okay. So my view since 1987 has been that Anderson's RBB mechanism superconductivity shows a fertile direction to achieve superconductivity at and above room temperatures. However, in an article in 1969, Anderson says room temperature supermagnet or superconducting ski is probably not. For one thing, so many diverse types of materials exist in nature or have been made in the laboratory that large, obvious effects would probably already have been seen. So he's, great phenomenologist par excellence who listens to nature always. So he was skeptical about the existence of hot superconductors, even after discovery of high TC superconductor. But however, in 1967, if you look at it, he says, but room temperature interferometers, who knows? He's probably thinks it is possible, maybe. So my obsession with hot superconductivity via broadband monoclophagy did bring appreciation from Phil after I gave a talk at Princeton on possibility of high temperature superconducting doped graph in a broadband system. Okay. Now, this is a picture postcard that I drew sitting in this beautiful aspen center in the hills near Colorado. So I was attending a program on, I think, superconductivity in 1987. So there was beautiful music from behind. There are flowers and bees and so on. So I saw in some petals the dx square minus y square orbital and p orbitals. So I sketched this and then I got very excited and sent it to Phil Anderson. And Phil has received it very happily, and then he puts it in some lecture that he gave in a conference. So it's pre-printed there. So he says, Bhaskaran being a Tamil, RVB becomes RVBs. If you look at the picture, I have drawn some bees and beehive and various systems known at that time. Later, Anderson told me that this aromatic ring compound that I talked about looks like K3C60. And then phosphorus to silicons looks like diamond, boron doped diamond, and so on. But the important point is RVB home is graphene. So this was my dream from the beginning, that perhaps we could reach room temperature superconductivity, hot superconductor at ambient conditions. Okay. Now this is superconductivity, just for the sake of maybe newcomers. If you take a material like mercury, cool it down at a temperature like few Kelvin, the resistance precipitately drops to 0. And then there is also a accompanying Meissner effect in which external magnetic field is expelled by the superconductor. Then it was very quickly realized there's a macroscopic quantum phenomena, and there is flux quantization and Josephson effects and so on. For example, if you, according to the theory of Ginsburg-Landau, and also according to London's rigid wave function hypothesis, there is a macroscopic wave function which describes the superconducting state. So it's like a single particle state of some object. Then angular momentum has to be quantized. That leads to flux quantization and so on. So these well known. Now, starting with mercury, there were enormous efforts over decades to reach new superconductors, create new superconductors with higher TC. And there was a quantum jump, 1986, thanks to Bednar-Muller's work of finding superconductivity around 30 Kelvin in lanthanum copper oxide when it's doped with barium. Then it jumped to IPCO and so on. The rest is history. The new superconductors came to the scene, K3C60, TA for compound yttrium, lead, nickel borocarbide, and so on. Now, in lanthanum hydride, LaH10, there is a claim that perhaps there is near room temperature superconductivity at 200 gigapascal. Now, just briefly to tell you, historically, there has been several mechanisms after the phonon mechanism of Bodin and others, Froelich and others, phonon-mediated superconductivity, Little's mechanism using excitons, Ginsburg mechanism, bipolar on, metallic hydrogen, and RBB dope Martin's waiter for reaching high temperature superconductivity. And on the experimental fronts, of course, it started with cuprates, and then organics showed a promise, but it stopped at 13 Kelvin. Then nickel borocarbide at 24 Kelvin. Then borides, some transition metal oxides, 40 Kelvin, carbon fullerene based system, 40, and ionic pnictides, 50, and so on. Then there are claims that hydrides under pressure reaches room temperatures, superconductivity. Similarly, there was a claim that this organic material, K3P terphenyl, exhibits superconductivity at 125 Kelvin. The famous silver gold nanostructure from friends at IAC claimed superconductivity at 300 Kelvin. But none of them are proved convincingly, but that's what I'm going to say is about that. So my friend Kopelevich wrote a beautiful article, and he called them elusive room temperature superconductivity. He recalled many historical things, which is what I will do today, and to tell you there is something going on which we have to pay attention to. And nature is smiling at us. Let us take it seriously and then look for superconductivity. So, more is different is that one of the themes of this, and I'm going to say height is different. And also I will tell briefly a story of how I joined force with Phil Anderson. Last year I told you, yesterday, how I joined Anderson's group. At the end of more than 2 years of stay in Anderson's group, I had very few publications, one with Anderson. I wasn't happy about my non-publishing mode. Anderson was, however, was happy with my stay, however. We discussed on a variety of topics seriously on daily basis. That was the fun thing. We used to discuss nuclear physics and something about machine learning and a variety of things, even in those days. And also I spoke to Anderson's graduate students, often translated Anderson's statements. It's well known that Anderson's remarks were very often incomprehensible, as Professor Ramakrishnan beautifully showed us in his first talk. It was a morning in early November 1986. Anderson walked into my office and placed a photocopy of an article and said, "We should work on this," and left. Then it was Bednarz-Muller's 1986 article on Cupriate superconductivity. On reading it, I got excited because I was interested in superconductivity. During the week, I developed a theory based on Jahn-Teller bipolar and presented it to Anderson. Anderson was patient and said at the end, "It's beautiful, but totally irrelevant for Cupriate superconductivity," and left my room. So I didn't understand Anderson. I thought he was getting old and continued to sharpen my theory. On mid-December 1986, just before leaving for Bangalore for the famous Balanced Fluctuation Conference, Anderson said, "Your theory ignores spin-half Mott physics, even though you drew my attention that it is a Mott insulator." The story is the following. It's good to have friends all over, whenever, wherever you are. T.P. Radhakrishnan was a good friend of mine. He was a graduate student at chemistry department of Princeton. He's a very distinguished chemist who retired, I think, recently from Central University of Hyderabad. So he was a graduate student at chemistry department. So once I told him about lanthanum copper oxide, he got a photocopy of a paper of Ganguly and Rao and showed me that it's a 1973 article on lanthanum copper oxide. And I showed that paper to Anderson. So the fact that it's a Mott insulator caught Anderson's attention. Then when he made this remark before leaving for Bangalore, made some subconscious rumbling in my mind, but I continued to ignore Mott physics. It was clear to me that Anderson did not have a clear idea of mechanism of superconductivity in a spin-half Mott insulator before he left for Bangalore. Anderson was, however, sure that my theory was wrong. It's amazing how nature helped Anderson to sharpen his ideas through a new data on lanthanum copper oxide that he saw at IAC Bangalore. Also a variational theory of quantum antiferromagnetism of spin-half Heisenberg chain that his friend and collaborator Maurice Rice presented at the same conference. So before I show how I entered, this is a story, fantastic story. Late Parthav Ganguly, my good friend from IAC, and Professor Rao, who is still active at the age of 91, very inspiring. So they wrote a paper in 1973 about lanthanum copper oxide. And you can see the remark that it's a half-filled band dx square minus y square orbital and metallic behavior and so on. I will not go into the detail. But what is fascinating is Ganguly and Rao continued their work on lanthanum copper oxide and new data on magnetic susceptibility, which did not show any cusp characteristic of antiferromagnetism. It showed some Pauli-like magnetic susceptibility. And since Anderson was familiar with C.N.R. Rao's work, thanks to the paper from T.P. Radhakrishnan, which I gave to Anderson, he visited C.N.R. Rao's lab at IAC in December 87 and saw the data on susceptibility. And his nature showed him a new way. He sharpened his ideas on RVB theory. Apparently, he prepared a talk in half an hour. The theory, gave a talk at the conference and predicted, based on this beautiful susceptibility, Pauli-like susceptibility measurements, that even though lanthanum copper oxide is a Mott insulator, it has some neutral fermions, zero charge fermions, and pseudo-Fermi surface. That was the beginning of the RVB theory. Then it was the first week of January. Actually, I didn't come to Bangalore because there was some issue there. So I was staying back at Princeton with my family, and then I started working on my theory of superconductivity. I waited for Anderson's return to convince him about the right correctness of my theory. So it so happened Anderson returned to Caltech rather than to Princeton. He landed at Caltech in the first week of January from Bangalore. And I called him over phone. And I wanted to tell him how my theory is developing. Before I started, Anderson silenced me and said, I have seen the light. And uttered 3 cryptic sentences. I have no time to go into that. It was electrifying and I too saw the light. I said, I understand what you are saying and will call you soon, and put down my phone abruptly. In 15 minutes, I gathered my thoughts and called Anderson and elaborated to him my understanding of his 3 sentences. He mumbled, you have smelled it right, absolutely. Thus began our long collaboration on RBB theory of high DC superconductivity. A friend often remarked, I became an RBB preacher. Okay. Now, this is an article that I wrote. It's a special edition of Pramana, some 100th anniversary of the Academy or something like that. So, new 5-fold way to new superconductors, where the copper route was shown by Anderson, Bednarz and Muller. Then there were pressure route, organic superconductors, impurity band superconductivity, diamond, graphene route, which I was involved in, then double RBB route, and so on. Basically, electron-electron repulsions in a tight bending system is a fundamental thing. And just before this, I wrote this article, I visited Tunisia, where my former student, Fethi Madhuri, PhD student, was working there. So he invited me for a week. So I told him when I go there, he should take me to Sahara. That was a condition under which I will come. So I go to Sahara, I'm sitting on the Sahara sand, some sand dune somewhere, and contemplating on hot superconductivity. What else is a better place to think about hot superconductors? So now I will switch gear and talk about historically superconductors that people seem to have seen, and it's elusive. In a beautiful article, my friend Yakov Kopulovich, a Russian who works in Brazil, he brings historical many instances: copper chloride, cadmium sulfide, polypropylene polymers, metal ammonia solution, amorphous carbon, tungsten oxide, surface in a variety of things, and show how they are unstable and elusive. Okay, now this is one of the systems which I got excited. Let me start with historically the first paper on possibility of high temperature superconductivity. It's amazing. This paper is from a chemist by name Ogg from Stanford. He was a very distinguished chemist. He was studying ammonia. He took liquid ammonia, and then it's like in salt water, like in water, sodium chloride dissolves very quickly and dissociates. So if you take liquid ammonia and put sodium chloride or lithium chloride, it decomposes into metal and ion and electric charge. So that's called liquid ammonia. So solvation takes place. Sodium ion, for example, gets surrounded by ammonia molecule. Similarly, electron gets surrounded by ammonia molecule. Now he found out some kind of Meissner-like effect at 200 Kelvin, occasionally, not always. So he had the fantastic insight to say Bose-Einstein condensation of trapped electron pairs before Cooper pair theory came, 10 years later, phase separation and superconductivity in ammonia. What Ogg did was, he took this metal ammonia solution and quenched it, and it became glassy. And he found out, the others had found spectroscopically, there is some tendency for singlets to be formed. It's as if 2 electrons come close by and form a spin singlet. And then he saw room temperature 200 Kelvin diamagnetism. Then he wrote a beautiful paper. And basically what happens is spin paired solvated electrons in ammonia compounds, what they start moving, and there are beautiful recent simulations which show that they form some kind of tubes in which they delocalize. But still, experimentally, it has not been confirmed. For example, if we talk to Professor C.N.R. Rao or P.P. Edwards, they will passionately say how they also see it occasionally, but they are not able to hold it in a superconducting state.
Yeah, Bhaskaran, I'll just interject for a minute. Bhaskaran?
Sorry?
Yeah.
Please.
So I think Yeah, this one was demonstrated, and the famous story is Mendelssohn. He shook that system which they showed the ammonia, then the superconductivity disappeared.
Correct, exactly. I will come to that. Yeah, sure. It's a transient thing. Yeah, I will. So then if you do a theory, there's very clear indications for pairing, very detailed analysis, and also there's a tendency for them to move in tubes. So what is remarkable is the insight that Ogg said that somehow electrons are forming a pair, and a pair of them forms like a boson. So there is bosons in condensation. The temperature scale was correct. This was Ogg's work, and apparently Ogg became very unpopular for the reason that Ramakrishnan said others could not reproduce it, it disappeared, and so on. It was elusive. Then Antoniewicz from Poland, he studied amorphous carbon. He found out Josephson-like effect, like he found out Fraunhofer pattern, as if there is a Josephson junctions, and with the magnetic field, the current in a very interesting way. Again, it did cuprous chloride, cadmium sulfide, and others, and saw nearly room temperature Meissner effect. Then Pablo Eskenazi and also this Koplevich have been studying graphite. In fact, I visited the lab of the Koplevich in Sao Paulo. He showed me the lab, and he says, I have occasionally seen room temperature superconductivity, and I have made sure it's not an artifact, but the thing is that I'm not able to stabilize it. So it comes and goes, so I do not know what's going on. So there are many, many papers in the recent times in journals about evidence for superconductivity, dwarf graphite, 300 Kelvin, 400 Kelvins, and so on. Then came this was an exciting time that in 2018, friends from Bangalore, Anshu Pandey and Thapa, his student, they reported anomalous diamagnetism and vanishingly small electrical resistance at ambient temperature in silver gold nanostructures. Anshu Pandey is an expert on making nanoparticles by chemical methods. So like a goldsmith, he makes nanoparticles of gold of 10 nanometer and embeds them in silver matrix. Then he studied some physical properties, and then it was Arindam Ghosh joined hands, and they also saw that what is fascinating is the resistivity nearly vanishes, not exactly to zero, but it fluctuates. There are lots of noise issues. And then the TC is 240 Kelvin, sometimes 300 Kelvin. Then what is fascinating to me, the smoking gun, is the temperature dependence of magnetic field, of TC on the magnetic field. This is something that cannot be explained by one electron effect, by any theory. So this has been always my test for superconductivity. If something exhibits Meissner effect and sensitivity of magnetic field to TC, there is something going on. Okay, this is something. Then another notorious or famous material, so-called LK99, a complex material which has this kind of structure. It was reported by this group from Korea that they saw ambient temperature and ambient pressure, room temperature, superconductivity, but which was again elusive. And the structure is fascinating. There are enough holes for them to accommodate the extra copper that adding, which I will use later in my theory. So they also reported, and then they was challenged, and then there was, now everybody laughs at it, and it has been forgotten. Okay. Now our own friend VPS Avana is always after new superconductivity. He also studied it, but he didn't see superconductivity, and many others didn't see it. Some people saw it, and it has been now put into the shelf. Now, my thesis is the following. It's clear that we are entering the realm of non-equilibrium phenomena and leaving the comfort zone of equilibrium thermodynamic phases. What we seem to have is statistical superconductivity. In some sense, it's not even a glasses, because there is something stable about glasses. Glasses relax very slowly. The aging is very, very years and thousands of years and so on. But here it's something different. So there is new physics still to be explored. So when a system is disturbed or taken out of equilibrium, presence of multiple metastable phases renders many competing and far from equilibrium phases realizable locally. For example, this is well known in the case of metallurgy and in water. fact, incidentally, those of you who are interested in learning about snow and ice, Kenneth Lipshart, he's a professor at Caltech. I knew him as a PhD student at Princeton. He has a beautiful website, Caltech. You can freely download this book on snow crystals and the physics of it. Fantastic collection of things. So it's known that ice has about 15 equilibrium phases. And it's known that water, 1H, and ice have open structure, hydrogen bonds, quantum dynamics of proton, although many structural reorganizations, water wires, and so on. And biological water is even richer. And also, it's a fantastic problem how water gets pumped up to thousands of meters in the tall trees, giant trees. It's not capillary reaction, something else. So water is a very mysterious thing. Look at the phase diagram of water as a function of pressure and temperature. You have the vapor, so liquid water, solid, and 12 phases of ice. I think there are more of them discovered. So it's very clear if you look at the configuration space and free energy landscape, there are many, many things going on. So water is the stablest thing, but then if you supercool water, you get ice. So depending on how you prepare the system, you could land up in some of the things. So this is a kind of thing that is, so given this, what is going on in superconductors, my belief, I will try to convince you. So the first question is, given solid state and quantum chemical constraints of our real world, do the above claims of high TC or room temperature make sense from BCS electron phonon point of view or RVB mechanism point of view? Okay, so now just to tell you what is the mechanism of standard superconductivity, you have Fermi surface, you have electron pairing mediated by phonon attraction, and then you have superconducting TC, which is given by this famous BCS expression. Now, phonon mechanisms, it was experimentally seen that TC was always less than 10 Kelvin, about 10 Kelvin in most of the material. And what is fascinating is Fermi energy is very large, about 5 electron on 50,000 Kelvin. Debye energy is 500 Kelvin. Deformation potential is 10,000 Kelvin. Somehow you manage to get a 10 Kelvin superconductivity. So if you want to use BCS mechanism and increase the TC, you can only increase the Debye frequency or increase the electron phonon coupling constant. But then it was shown by Macmillan, Anderson, P.W. Anderson, and Cohen that from structural stability point of view, you cannot increase all the things at will. There is a constraint, and phonon-mediated superconductivity cannot exceed 30 Kelvin. That was a scenario. That's when RVB theory came. So I will give a 5-minute pedagogic introduction to resonating valence bond theory. So which is very simple at level of conceptual and simple ideas. Imagine you have a hydrogen atom forming a hypothetical 3D lattice. This was Mott's thought experiment. So when the lattice parameter is comparable to Bohr radius, the 1s electronic state where the electron is residing will overlap and electron will tunnel and form a tight bending band. Since there is 2 electrons in every K state, you have a half-filled band. That's it, it's a metal. Now Mott said, let me do a thought experiment in which adiabatically expand the lattice and make the lattice parameter larger than Bohr radius, much larger than Bohr radius. Then what will happen? Then electrons will not quantum mechanically tunnel and form a band, because when it tunnels, when it creates an extra charge in the neighbor, and also it has to unplug itself from the nucleus of the parent nucleus. So it causes an energy. So it's very clear when the lattice parameter is very large, electrons will stay home, stay put, and have random spin. So it's a very highly degenerate state in terms of spin configuration. But however, in terms of charge, it's very simple. Nothing can move. So if you want to create an excitation, you have to remove an electron and go across a gap, which is called a Mott-Hubbard gap, and then get excitation. But however, it was recognized by people like Anderson and others that if you think about real situation where for example, copper atoms in lanthanum copper oxide are not that separated, there is a repulsion among electrons and which prevents them from forming a band. But however, electrons will not sit at home. They will undergo quantum fluctuations. For example, if you take 2 neighboring sites, which have 2 spins, the opposite, it can occasionally undergo a quantum fluctuation to create a doubly occupied state and empty site, and then come back to exchange configuration. So this is called a kinetic or super exchange. So you gain energy. So quantum fluctuations gain energy, and this is called exchange energy. But what is interesting is Pauli principle selects singlet from the triplet, because if you have 2 spins which are parallel, Pauli principle will tell you that you can't have super exchange. So this is encoded the language of Heisenberg exchange. It says that S dot S, J, which is antiferromagnetic. Now, if you take this attitude, do this in a simple-minded way, what you could do is you will find that two electrons in neighboring sites will form a spin singlet. They will resonate and gain super exchange energy, and then they can form various valence bond configurations. But however, they can move around. So there is a motion dynamics, and what you see finally is some antiferromagnetic order with some kind of quantum spin fluctuations. So then it was, if you go beyond this half-filled band, suppose I manage to remove some carriers from the band, then I create empty sites, then that's called doping. Then the singlets will move and bodily carry singlets. So, and that is the beginning of superconductivity in RBB theory. So it's somewhat like, this is where Anderson's inspiration came from, Pauling's resonating valence bond, where he said there are 6 carbon atoms and 6 2pz orbital, there are 6 electrons, they resonate like this. So Anderson applied it to lanthanum copper oxide in an extended system and said, here you have a possibility of superconductivity. I'll not go into the detail because I'm talking about something else. So the heart of RBB theory is the starting point is not a Fermi sea, a paradigm shift to Mott insulator and doped Mott insulator. And there was support from transports and various things. So the message from resonating valence bond state theory is, the way the caricature that I gave you, what happens is you have a Mott insulator where electrons, neighboring electrons, because of super exchange, tend to form a spin singlet and they start moving around. But in the absence of doping, only spin current flows, no charge current. So it's a neutral superconductivity, so to say. Then you remove this, you dope the system, then singlets, bodilies can move and carry charges. So that's a very simple mechanism that Anderson came up with in his famous science paper. So the idea is super exchange is a glue. Fraction of electrons participating in superconductivity is not h cross omega d by Fermi energy, like in the case of Fermi sea and phonon-mediated pairing, but proportional to the space available for singlets to move, which is x. And further, superconducting TC is proportional to x times j. This is it. It's a very heuristic picture, no microscopic justification at that time when Anderson wrote this famous science paper. And he made many other beautiful statements about variational wave functions and so on. But this is a message from RBB theory that you have a new paradigm, Mott insulators at seats of high temperature superconductivity. If only you can have that and create some doping, do some doping, you could in principle have superconducting TC, which is of the order of J. If you take cuprate, J is about 0.13 electron volts, so more than 1000 Kelvin. So X is about, if you take 0.1, then it's about 200 Kelvin, so it makes sense. So you have all of a sudden jumped from a scale that you are limited to Fermi sea and so on by phonon mechanism. You are liberated to new regions where superconducting TC is proportional to J, which is a local chemical singlet energy scale, and the X is doping. So I was fortunate enough to be there in the right place with the right person in 1980 during that time. So we wrote a paper with Zhou on a mean field theory, which brought out many of these features. And then Anderson and myself, we wrote a paper on emergent gauge fields. And then we wrote some other paper and so on. So the important point is the Mott insulator at half filling is not a superconductor, but there's lots of singlets, there are resonance. Okay, now let me come to the next one. So this is the model that Anderson used in his theory. He said, okay, so how do I describe Mott insulator? That's it's well known that it's described by Heisenberg antiferromagnetic Hamiltonian. Once you dope it, he used what is called TJ model. TJ model was used by many people, including my friend Wallace and Chow and others. That what you do is you take Heisenberg antiferromagnet and say that if there is a hole that can hop to neighboring site, then now remembering that at no time there can be double occupancy at any given site. There cannot be real double occupancy. So it's a simple looking Hamiltonian, but heavily constrained. So this is a TJ model, which has been bothering us for the last few decades. We know how to solve it qualitatively with the help of experiments and find solutions approximately guided by experiments and so on. But rigorous solutions are absent except in lower dimension, 1 dimension, for example. So now let me talk a little bit about this RVB theory. From the model point of view, if you take one-dimensional Heisenberg model, Hubbard model, it's a fascinating system. It was solved by my good friend Lieb and Wu many years ago. He found that even an arbitrarily small repulsion in a 1D chain will make it insulating. That's because in one dimension, an electron is like a traffic jam in some road. You one car stops, everybody stops. So in one dimension, the repeated scattering will amplify even a small repulsion into a large repulsion, renormalize it, and make it look like a Mott insulator. Now, if we study this one-dimensional system, I have a phase diagram U over T, the bandwidth, the normalized repulsion, as a function of number of electrons. One corresponds to 1 electron per site. So there is a line which says a Mott insulator. Then you can dope it with holes or electron. And what is interesting is you can look at the physics of it in a very accurate way using Latimer liquid theory, bosonization, variance, and so on. You see enhanced singlet correlations as you move away from half filling at arbitrary U and so on. So we understand 1D Hubbard model quantitatively and qualitatively extremely well. Now, what about 2D Hubbard model? Now that's where the problem lies. The 2D Hubbard model is what we are facing in cuprate. So we have a Mott insulator, and then there are very good now theories, approximate theories, say that there is dynamic Mott localization and source of resonating Van Allen sheet. But the most important point is, it's like Indian democracy. There are many, many competing phases, many, many competing forces. So nobody wins finally. So that's what happens in most of these models when you do theory. But however, there is something called an optimal doping in which superconductivity seems to be. So if you take care of competing orders like charge stripes, spin stripes, I will not go into the details. So this is a major problem in a strongly correlated system. A strongly correlated system and repulsion is very liberal. It encourages everybody and somebody wins. And if you are looking for superconductivity, occasionally we win, very often we lose. Now, when you go to 3 dimension, similar thing happens. I will not go into the detail. Okay. Now, it is at this point, being obsessed with resonating valence bond state theory, I was looking for broadband Mott localization or a situation where J is very large. Then I found out graphene showed the way. So because Pauling said graphene is described by this wave function, so I developed a theory in 2002 in the context of MGB2 and showed that you could have very high TC superconductivity over doped graphene. It was an approximate theory. And my good friend Doniak from Stanford and his student, former student Anna Bloch-Schaefer, they took the Hamiltonian I gave, and then did a wonderful job and found a D plus ID superconductivity with a scale which was 3000 Kelvin, embarrassingly large. Then I was fortunate to get Shanai from IAC visiting me at Bangalore Math Science. So he was good in his student. They did a wonderful numerical job of variation of Monte Carlo. They said what GB and Doniak and Anna Bloch-Schaefer said is right, but now instead of 3000 Kelvin, you have 300 Kelvin superconductivity. It was confirmed by Wang, Nandkishore, and Kiesel, Gu, and others on a variety of numerical work. But this is at optimal doping. But once you look at underdoping, there is a problem. Now, this is just a story about graphene. I will briefly tell you. It's a honeycomb lattice, so-called Dirac metal, and so on. And then you have, as you increase the Hubbard U, you have a Mott insulating state. And then graphene, doped graphene, is not in the Mott insulating regime; it's in the conducting regime. How does superconductivity come? So that's where this beautiful work by Shanai and Pathak, they did a wonderful variation Monte Carlo, state of the art. What they did was they took variational wave function and did the best calculation and found out superconducting order parameters changing in this fashion, like in cuprate as a function of doping. And they inferred from various things. The superconducting TC is between 200 and 400 Kelvin. So it was a state-of-the-art variational calculation at that time. Now people have gone to much bigger sizes and matrix product states and so on. What they find is, it is true that there is superconductivity at optimal doping, but under doping it's dominated by competing orders, as it's very clear from experiments in cuprates and other systems. So we have to avoid competition. And what is also very fascinating was the scale of TC was almost like T over J 50, which was like X times J in the case of RVB theory. Okay, now we come to rationalize some of these observations that friends have seen which are elusive superconductors. I will try to rationalize that if they are possible, it's worth spending the time and effort to stabilize them. So we perform a thought experiment and make free-hanging 2D monovalent metals, copper, all. Now, it's very fascinating that if you do a very simple theory of planar copper or planar silver or planar gold, the simplest model that you have is a 2D Hubbard model on a triangular lattice, because you can ignore the higher bands. So it can be determined on tight binding model, this is the Hubbard U. And then when you look at the phase diagram, they'll all become ITC superconductors. That's my finding. But why don't we see it? But then that's where the competing orders come. So I did a theory assuming that all the copper, silver, and they're all rigid, they don't move. But in reality, they form singlets and they form valence bond and they prevent delocalization. Many, many things happen. Okay, now let me again mention about why, while copper is not, or sodium, or silver or gold is not a superconductor in 3 dimension, how can it become a strong correlation physics can come in lower dimension? So that's where the dimensionality becomes very important. Birds or mosquitoes do not experience any traffic jam because they live in a 3-dimensional world. But cars experience traffic jams, even 2 cars. Ants follow rules and hence no jam. So 2 dimension is in between. It's well known that probability of random walk returning home in 1 and 2D and 3D are very different. So, okay, now with that understanding, let me rationalize the possibility of rationalizing the superconductivity, transient superconductivity that friends continue to see at Bangalore. In fact, whenever I go to IAC, I visit Arindam's lab and I visit Pandey's lab and talk to them. They are silently working on it and they are improving the statistics. And it's not that originally there was a lot of noise that saying what they are seeing is a noise, and then there is some problem with the shorting and so on. Now they have taken care of all those things. It seems to be genuine phenomenon, but except that it has its own mind. I see superconductivity today, I don't see it tomorrow. So what's going on? So what I did was the following. I looked at the So if you look at some of the structures, this is how it looks like. So, for example, if you look at this gold silver nanoparticle, was done in some other context, they form there is an FCC lattice, and they form this kind of structures, nanocrystallites, and then junctions and so on. But what is interesting is the silver nanoparticle that Thapa Pandey did also is like that. If you sorry. Okay. Now, so what is it was you have a silver and gold or 3-dimensional system, which are 0 temperature superconductors for practical purposes, unless Ramakrishnan one day discovers that it has also very low microequivalent superconductivity. So, but now if you look at this material and if you look at the structure through electron microscopy and so on, there are faults. I'm finding faults with them. That is, the FCC structure will have ABC, ABC, ABC stacking, but occasionally you see A intervene, so they're called stacking faults. And Aristotle is supposed to have said long back that between 2 correlated faults lies virtues. So between 2 faults lies high TC superconductivity. What I do is I take this stacking AA, B, and CC, and then do a band structure calculation. I find an isolated 2-dimensional band embedded in the midst of a 3-dimensional band. Then once I have 2 dimension, I can go to 2D Hubbard model and parameters and find a possibility of RVB state and superconductivity and so on. So similarly, quasi 1-dimensional bands close to half-fielding exist in silver gold nanoparticles. I can see it from the structure. So fault lines emerge at grain boundaries. So they are supposed to. So what you have is you have RVB islets or islands distributed throughout the silver gold nanostructures. And it's known that from various theories that if you have a metal containing superconducting islands, there can be proximity effect induced 3-dimensional superconductivity, but it will be very glassy and weak. So proximity creates an RVB islet web of granular ambient temperature superconductivity. This is my theory. And so I put it in the archive and then singlet reservoir theory. And in fact, it got accepted in a journal, International Journal of Modern Physics. I say that a single half-filled band crossing Fermi level provides a number of okay. This is a very interesting thing, that if you look at silver, sodium, and potassium, it was Hauser who said that it's not a simple metal. There are spin density and charge density waves competing, and finally they are killing themselves, and you have a Fermi sea. And I have looked at it carefully and said that in addition to charge density and spin density, there is also superconductivity competing. Everybody loses, finally Fermi liquid wins. So I have shown it in my paper. Now, a carefully designed perturbation could deconfine a confined superconductivity. So that's what I have said, these various structures and so on. So in the same way, I have looked at this famous apatite, the material LK99. And if you look at the structure carefully, there are channels there in the way the structure is made, in which you can have neutral chains of copper atoms. And once you have neutral isolated chains, they are Spinhoff-Martin insulator thanks to work by Lieb and Wu. And even though the bandwidth is very large, they have a large exchange coupling, like 2 electron volts. So the J is 10 times, 15 times that of cuprate. But however, they cannot support superconductivity even if they are doped, because they are one-dimensional. There will be strong fluctuations. So in apatite structures, network of interstitial columnar space runs parallel to C-axis in the AB plane. They accommodate excess copper as neutral copper clusters, chains, and planars there. So they are our emergent antiferromagnetic Martin insulator. Then and so on. So a major challenge to superconducting orders, the real material is competing phase, as I said earlier. Okay. Now I think, how am I doing with respect to time?
I think you have about nearly 15 minutes left. You started late anyway, so.
Okay, good. Then I will finish in 5 minutes.
Okay.
And then we can have a discussion. Is that all right?
Please, Bhaskar, go ahead.
Wonderful. So, in fact, if you look at the history, I will say cuprate is a failed room temperature superconductor, because depending on the system, whether you have a single layer material or double layer material or triple layer material, the TC varies enormously. It's not like an isotope effect. Like if we take single layer family of cuprates, the lowest TC is 5 Kelvin, the highest TC is 90 Kelvin. Who decides that? Now it's very clear the single layer lowest TC material has lots of octahedral distortions. So competing orders like charge type and string type overwhelm and superconductivity is suppressed. Now when these octahedral distortions are relieved by structural chemistry or solid state chemistry, then superconductivity raises its head and you get 90 Kelvin superconductivity. That's what happens when you have 3 layers. The middle layer, which is protected, exhibits without any distortion high TC. So, and also there has been claim that of observation of 200 Kelvin superconductivity cuprates in the past. And of course, people withdrew it because others could not reproduce it. I tell them, please repeat the thing carefully. See, we may have been able to go to Moon and Mars and so on, but still we have no nanoscopic control. So there is still more room to get improved, at the bottom. So according to my calculation, intrinsic maximum TC of cuprate is 250 Kelvin within the RBB theory at optimal doping. But occasionally people have seen it, but then it disappears. But a stable superconductivity is around 165 Kelvin, maybe under pressure. Under ambient conditions, about 130 Kelvin. Now, in another paper I wrote, there was a fantastic result about silicene, again, which the people saw signature of room temperature superconductivity. It was elusive and people withdrew it. So what I did was I did a theory. If you look at silicene, it's like graphene, except that the bandwidth is reduced by a factor of 3. So if you do a simple model for silicene, it looks like graphene model, but if the bandwidth is reduced by a factor of 3, and the Hubbard U is not reduced that much. So when I do a theory, I find silicene is a potential room temperature superconductor. I quoted in my paper about 6 experimental evidence. I was invited for some conferences and so on, and it was very exciting. Then the people lost interest because they always like white-collar job, carbon and so on, and a dirty thing. People don't want the reproducible neat results. Then you have to pay a price for it. You will miss okay. So before I thank you, let me go back, and I wanted to tell some more things. So, for example, this is a very important point. Once IAC friends did this work, there was a lot of interest in the international community. There was a lot of criticism, and many people tried to reproduce it. ISA Pune, they did laser ablation, and they didn't see it. Of course, laser ablation will not create nanoparticle of gold embedded in a silver nanoparticle embedded in a gold medium. It will create alloy. However, IIT Mandi friends, they saw by some sputtering method, occasionally signals for room temperature superconductivity. Again, it was very transient, so they gave it up. Then Bhubaneswar Delhi collaboration, they saw by ion implantation method, they saw, in fact, what was fascinating, not 100 Kelvin but 1 Kelvin superconductivity, which is already fascinating because silver, the Tc is 0, gold Ct is 0, but getting 1 Kelvin is like 1 by 0, which is infinity. But then they gave it up because there was no international encouragement, and people started laughing at this whole thing. And except for Bangalore, I do not know who else is working on it. They are continuously working on it. They're improving their statistics and so on. Now, I encourage some friends at IIT Madras to work on it. They did something and then they also gave up. Then Raghavendran is my old collaborator, and Bosco Emmanuel, both are electrochemists. So they have some way of stabilizing these kind of structures by electrochemical means, so which is much better in many, many ways. So we are trying that. So the message is that we are entering the realm of sorry. Yeah. So we are entering the realm of far from equilibrium phenomena and leaving the comfort zone of. So this is well known to biologists. See, biology is a highly regulated non-equilibrium phenomena. An insect, if you look at it, it dies, then you cannot do anything about it. Bacteria. So it's very unstable. Lots of things are going on. See, now solid state, like if you look at sodium chloride or quartz crystallines, and so stable and so rigid. But now we are entering a completely new. Well, people working on batteries know this. For example, people working on batteries, they know that the ionic conduction corrodes them, and then things change with time very fast. So they have no control. So that's one of the reasons why many people are working on batteries. So battery is not for superconductivity. Here we have a situation of superconductivity. Definitely there are signals that it's happening. So I think there is room for room temperature superconductivity from theory point of view. But however, what we seem to have is a statistical superconductivity or probabilistic superconductivity. Some sense it's beyond glassy phase. There's new physics still to be explored. So with that, I conclude my talk, and thank you for your attention. I'll be really happy to answer any questions.
Thank you, Bhaskar, for a wonderful talk. I think it always, it amazes me the way you present all the complex system in one common format and then tell us about, one system where you go and explain really nicely. And I think this is what motivates all the students. I was motivated by your talk when I was a student, and so on. I think it's really nice to have you give this lecture. The other thing which you mentioned very clearly, it's not the high TC is alone is interesting. The high TC material brings out new physics, like your resonating valence bond. Then you see that unusual Fermi surfaces, marginal Fermi liquids, non-Fermi liquids. It brings out every time a new superconductor. This one is discovered. It brings out really new physics, and I think you are always telling us that. And when I saw this probabilistic and statistical superconductivity, I wish I have to just go back to my graduate state and see what we can do to realize what you are saying in the laboratory. And it's really a thought-provoking lecture and wonderful lecture. Thank you very much. And I think this talk now open for questions and comments.
Thank you, Ramakrishnan, for your kind words. So I will.
Any questions from the?
See, I always say that, whenever I give a talk, a colloquium somewhere in India, there are no questions from the students. But once they come out of the hall, the students gather around me and they start asking questions. So I wish I can be there and go out of the hall.
No, I think you should come to ISER and talk to these younger students. They are unafraid to ask any questions.
Oh, I see. Very good. Yeah.
Very, very, very nice atmosphere. This is what I miss in TFR, and I'm enjoying it here.
Since Ramki, yesterday I briefly mentioned about your discovery of low temperature superconductivity in bismuth.
Yeah.
And you may recall that I say that it's a fallen room high temperature superconductor.
Yeah.
Because there are very good indications that a small perturbation increases Tc from half a millikelvin to 10 Kelvin. Amazing.
Right.
And according to the theory that I developed, nothing will prevent it from even happening at 150 Kelvin.
Right.
So that's when Phil Anderson was very excited by my theory, and he gifted me that structure of bismuth compound. So that structure was gifted to him by Vanier, and then he gave it to me. So there is a lot of room for room temperature superconductivity. Plenty. The question is, we'll have to have a good control.
Exactly.
I think the battery analogy is which is good, because we have been struggling with batteries and improving the thing. So many challenges. Anything that involves time-dependent phenomena, things can be very, very challenging. But we are there. I think very soon we will discover.
Any other questions or comments? Just let me make one question. It is there is a question from the audience. Jayesh, can somebody read this, please?
Yeah, Jayashree says something. Yeah.
Yeah. Senior secondary school teacher, how do you explain the causes of superconductivity to class 12 students? Bhaskaran?
Oh, wonderful, wonderful. How do you explain? Yeah. It's a very, very class 12 students. So, if I think I will start by talking about liquid that flows. Viscosity. If you take honey, it is a highly viscous liquid. If you take water, it's less viscous and it flows. Imagine electrons in a solid flowing. As the electrons flow, they encounter impurities, they encounter lattice vibrations, they get scattered. So normally you must see a resistive state, which is what you see normally in metallic, copper, or anywhere. There is finite resistance. But superconductivity, the very fact that all of a sudden the resistance vanishes identically, it becomes zero, is something that you cannot explain by classical means. So that is where you have to tell the student that you'll have to take quantum mechanics very seriously. Even though we don't understand quantum mechanics, we'll have to understand the rules of the game. In fact, it was Feynman who said, please shut up and calculate. You don't know the rules of the game. Don't think about it. It will become confusing. So that's what BCS did. They did a theory and calculated, and they found various things. So, I'm not telling that you should tell the students to shut up and calculate, but I'm telling that it's a fascinating natural phenomena that occurs on the table where resistance vanishes identically. So it's very counterintuitive to our common thinking. So you'll have to impress upon the students that in nature there can be counterintuitive phenomena. For example, it's all over around us. Our very life is counterintuitive. I can understand ferroelectricity, I can understand maybe superconductivity, but how do I understand life? There are many, many counterintuitive things. When it happens in a tiny material like mercury, you get excited. But life is full of surprises, and many, many things are happening. So, please don't think I'm evading the question. I'm just saying that you'll have to tell the student that the experimental fact is superconductivity goes on also zero. In fact, it's very good you asked this question, because there is a paper that Einstein wrote in 1920 about theory of superconductivity. Sorry, I don't have a reference. You can do Einstein put it in the archive, in the sense somebody translated that paper and put it in the archive some 10 years ago. It's a fascinating paper. Einstein says, here is a phenomenon of superconductivity. It's a challenge to theorists, because our conventional wisdom says that electron that's moving will get scattered. There will be always a Ohm's law, and these various simple theories tell you that it will be resistive. Then he says, how can I understand it? Then he makes some suggestions about correlated motions and so on. At the end, he says, I'm giving up. I cannot explain it. But he was far ahead of his time in his paper. He says so-called correlated motion and ring exchange. And then he also makes a very interesting statement at the end, which is very revealing. He says, now I will think of normal state of a metal as a perturbed superconducting state. Somehow I should take superconducting state as a reference and think about the normal state as a perturbed state. In fact, that's what is happening in cuprates. The cuprate, the normal state is supposed, as Ramakrishnan pointed out, it's an anomalous state. It's a perturbed superconducting state. So, many things happen. So I do not know how to explain to a student, but the fact is, please tell him it's very counterintuitive. It's as if a liquid is flowing without, like liquid helium, that's what happens. It flows without any viscosity. So it needs quantum principle to be explained. And it took 50 years for people to understand it and explain it. And even now, there are many, many issues to be understood. Thank you.
Okay.
Is there more questions? May I say something?
Yeah, please. Yeah, Professor Alvalia. Yeah.
I have just to say one thing, Professor Bhaskaran, you took us on a peak. And, when we reached there, we were feeling giddy, that a sweep which you presented. I just want to really ask one thing, and that is this, that if you want to encourage somebody to take up a problem of this kind, what kind of preparation actually is needed? Because that is what is happening, that today students do not have that kind of patience to persist with these kinds of problems.
So I'm not an experimentalist, but what I will suggest is one should take this as a hobby or a side problem. One can be doing some regular for example, metal ammonia solution. Apparently, it's fairly straightforward. Getting ammonia solution and then dissolving lithium chloride or sodium chloride and quenching it. And Ogg did it in 1946. And he saw, so I don't find anybody repeating it in India except that was Rao's group. So there is no reason. In fact, I gave a talk at Bangalore some years ago about possibility of room temperature superconducting. I suggested that government should invest a lot of money on encouraging young people to go into these things. For example, amorphous carbon. I mean, the burnt wood is a piece of amorphous carbon. So Antonovich saw some Josephson-like effect in amorphous carbon. So why don't we ask our student to try that? Even if 1 in 100% find something unusual, it will be worth taking the effort. Otherwise, they will understand something else about carbon. So there is more in carbon than meets the eye. So I think we should encourage them to do some experiments, simple experiments. For example, from my point of view on superconducting, there are many, many things happening these days, topological insulators and a variety of fancy things related to battery, various things. But good effort to see this, some of the LUC superconductors as a part-time job will be wonderful.
Thank you.
Is there any other questions from anyone?
Professor, I have a question.
Yeah, please. Yeah.
So thank you. This is Dr. Ajay Thakur from IIT Patna.
Hello.
So it has been a very nice talk. I just wanted to know that, like in cuprates, there has been a lot of efforts trying to decouple the C-axis conductivity, like by making larger and larger unit cell structures. So, like, what is the crucial reason for doing that? Like, why do we need to really decouple the C-axis conductivity? And can this be actually extended to other structures? Because at some point of time, people gave up on cuprate systems, right? The highest TC is somewhere around 150 or so, right? So can we try it in other systems like Aurevillius phase or Dion-Jacobson phase?
Yeah, very good. Very good question. See, from the beginning, we are stuck to a lower two-dimensional material in lanthanum copper oxide. It's weakly coupled to planes. So whenever there is a bilayer, somehow the two bilayers cooperate and increase the TC. Like IPCO, the minimum TC is 90 Kelvin. Tri-layer, it's even higher. So that's why people emphasize on what is happening on what along the C-axis. How C-axis stacking helps in superconductivity. Is it by reducing competing orders or by something called pair tunneling mechanism? According to this mechanism, there is a mechanism due to Su, Beatley, and Anderson that when you bring two cuprate layers together, because of the anomalous normal state, single electron tunneling is inhibited, whereas pairs can tunnel. So that can self-consistently feed onto it and increase superconductivity. That's called pair tunneling theory. So it's the fact that it's similar thing happens in one-dimensional, quasi-one-dimensional superconductors in organics. There is pair tunneling between chains. So if only one can find out a three-dimensional superconductor, it will be wonderful. But so far it has been always, you have somehow superconductivity is restricted to two-dimensional system. For the reason I was saying that electron correlation effects become dramatic, they show up as superconductivity in two dimension rather than in three dimension. In three dimension, in some synthetic materials, I'm sure one day people will see superconductivity. For example, this hydrogen sulfide and other materials under great pressure, not under ambient pressure, or three-dimensional, genuine three-dimensional system, they exhibit superconductivity. In fact, in H2S, it has been experimentally confirmed. There are issues about Rangada system, 300 Kelvin, but there are systems at 270 Kelvin, which everybody agrees. They are three-dimensional systems, but unfortunately, we'll have to apply pressure. So as you said, there are other phases like Orville phases and so on. They are worth exploring. So there is a lot of room for exploration. I agree with you. And there is, I think, cuprate has shown us a way. Similarly, carbon and liquid ammonia solution, metal ammonia solutions, and so on. So it's worth exploring other things. Yeah.
Yeah. Okay. Thank you.
So, if there are no more questions, let's thank Bhaskaran again for a wonderful talk. And I think we'll move on to the next part of our agenda.
Thank you.
Yeah. Professor Aluwalia, you have your hands up. Okay. So I think we will move on to the panel discussion now, or
Yeah, please.
yeah. So I think let me. Who are the members? Let me invite. I think. See, condensed matter is. It's always brings out surprises, with both from the fundamental point of view as well as the application point of view, and particularly this what they call it a second quantum revolution, which is happening in the last, let's say, even more than a decade, and in the last 5 years, it has taken unprecedented expansion in the case in the case of applications. You must have heard about this quantum revolution brought a lot of things into the system, and some of them are really coming to the market. The government of India has also realized the importance of the second quantum resolution and revolution, and I think about 3 years ago, one of the hub, which you call Section 8 company, was uh, constituted and also formed in ISA Pune as a patron, which is called the iHub for Quantum Technology. This was a part of one of the 25 hubs, which was generated under National Quantum National Mission for interdisciplinary cyber physical systems. And when I retired from TIFR and I wanted to come to ISER primarily to start the very low temperature activity, but also I was interested in participating this Section 8 company, which is supposed to produce quantum technology products, which will be very useful for our country. And so there is a modest beginning here, but I think this panel discussion is to see how we can harness most of the things which quantum mechanics tells us to go ahead and do this, because we are in an era when I studied quantum mechanics, with the entanglement state and the superposition of states and so on, which was always on the theoretical level. But now the physicists have tools to control these states, and they are talking. They have demonstrated many things like quantum communication, quantum computing, quantum materials and devices, and also we need to look at the enabling technology. So these are the four verticals in which the National Quantum Mission has already awarded 4 centers, and I hope that this would really take up, in a grand way. And a small way began at IISER Pune, and this 4 centers, which are at IIT Madras, IIT Delhi, IIT Bombay, and also IISc, would take it to greater heights. With this small introduction, let me first invite Professor T.V. Ramakrishnan, who has been, as
Sir,
a pillar of.
may
Yeah,
I say something?
yeah, sure.
For this panel discussion,
Yeah,
we have Professor Kia Dharamveer as a moderator.
sure. Okay.
So may I
Yeah,
request
sure. Please go ahead.
Sapna Sharma to please introduce her
Yeah,
and introduce the panel, and then we
right.
will start.
Sure.
Yeah.
Thank you
All
very
right,
much.
sir. All right, sir. Thank you, sir. Uh, so the next session is a panel discussion, and we are going to have a panel discussion on the topic opportunities for doing small science. And in this panel discussion, the panelists are Professor T.V. Ramakrishnan, Professor G. Bhaskaran, Professor S. Ramakrishnan, Professor Arun Grover, and Professor Deshmukh will be there. And moderator is Professor Kia Dharamveer. So before we start, I would like to give a brief introduction of Professor Kia Dharamveer ji. She is a distinguished physicist with over 40 years of teaching and research experience. Professor Kia Dharamveer began her career as a teacher assistant at IIT Kanpur, where she completed her PhD and later held a professorship at Punjab University, Chandigarh. In addition to her academic role, she served as a dean for foreign students and contributed to the establishment of university's interdisciplinary nanotechnology program. A passionate researcher, Professor Dharamveer's work on nanomaterials and solid-state physics contributes to be a widely cited. She has authored over 140 research papers and mentored numerous graduate and doctoral students. As a socially conscious scientist, she founded the Society for Promotion of Science and Technology in India, aimed at promoting scientific awareness and literacy across the country. She continues to inspire students and researchers with her dedication to both scientific programs and social causes. We welcome you, ma'am, and glad to have you with us on this platform. So over to you, Professor S. Ramakrishnan, for further proceedings.
Sorry for the earlier remarks, but I think let me just invite Professor T.V. Ramakrishnan to say about his understanding and what he feels one can do. Professor Ramakrishnan,
Yeah,
T.V. Ramakrishnan.
all right. I'm here. I'm just.
Can I please? Sorry,
Yes.
TVR, can I please say a few words?
Yeah,
Yes,
Yeah,
sure.
yeah, of course.
Ma'am, sure.
Sure, please.
You are the moderator.
Yeah.
Yes. So what I was thinking, the way we will proceed is we will go one by one in this order. Professor T.V. Ramakrishnan, then let us have Professor Arun Grover.
Yeah.
All of you for 5 minutes, please, because Professor Grover may have to leave early. Then we will have Professor Bhaskaran, then Professor S. Ramakrishnan, and Professor P.C. Deshmukh. Please discussion. And since all of you are who's who in condensed matter physics, I request you to give me 2 minutes to remind of the well-known 4 slogans of P.W. Anderson, since we are here to commemorate P.W. Anderson. So his 4 slogans, which were given as he was presenting his case against the superconducting super collider, and this was in 1987. We picked it up from an article. I'm grateful to Professor Aluwalia for pointing out that article to me. So the 4 slogans are: number 1, science can be fundamental without being irrelevant. And this is in the context of high energy physicists lobbying for their large projects. The second slogan is money is important, but manpower and education are more so, and money affects these. So all of us agree with that, I suppose. The third slogan is the term spin-off should be erased from the language. Again, in the context of high energy physics large projects. And number 4, the golden eggs are very seldom produced by golden geese. And this, in the context of the fact that funding is often in favor of large unitary centers conducting large, expensive projects. However, really new things in the area of superconducting materials, such as molybdenum chalcogenides, heavy electron superconductors, high TC oxides, etc., came from smaller places. A fraction of the budget earmarked for the superconducting super collider could restore the prominence of the few universities and labs engaging in innovative fundamental small science. These are words of P.W. Anderson. So now let us start the discussion in the context of here and today. So over to you, TVR.
Okay. Yeah, thank you very much. I'll try to stick to 5 minutes. I do believe, I think, can you see my slide?
Yes, yes.
Okay. First, I want to say that my understanding of small is that relatively small funding is needed. I would have preferred a title something like tabletop science, but doesn't matter. But I do want to emphasize the fact that though relatively small funding is needed, it is not small in terms of the significance of the science. So it is not about insignificant science, but it is about relatively inexpensive science. Then the answer to the question implied is, the question implied is, are there opportunities for doing small scale science in India? My answer is yes, there are. Unfortunately, what I want to say is only a guess, because I'm a retired theorist, not an experimentalist. I'm not in touch with ground realities, in particular the bureaucratic landscape, which apparently is very constraining and disheartening to many people. However, I feel optimistic about the opportunities simply because path-breaking and excellent high-quality science has been done by some, I would say, mad people with no funding agencies. And the examples which come to mind are J.C. Bose, C.V. Raman, and Shambhunath Dey. Shambhunath Dey discovered cholera enterotoxin with absolutely no facilities. He was a practicing doctor in a medical college in Calcutta. And that was probably at the time when there was hardly any funding for science anyway, in the early 1950s. Now, let me comment on that. One will very legitimately say, well, that was long ago. What are the possibilities today? I do not know, but I'm just guessing, and my guess is described here. The possible route is first emphasis on professionalism. This is very important because one cannot simply say that, well, I want to do something very great. I mean, it reminds me of some incident in IIT Kanpur. One student stood up and not in IIT Kanpur, but somebody in Aligarh Muslim University, he stood up and said, "Sir, how can you win a Nobel Prize?" Well, I mean, that's a good question, but I don't know the answer. But one thing one can do is to have a very high quality professional preparation for the particular scientific enterprise you want to undertake. Now, there is no substitute for this. Second is what C.V. Raman used to call the 100-watt mind. C.V. Raman functioned in an era which is difficult for us to imagine in reality. There was, of course, no funding agencies. There was hardly any money. There was active discouragement for scientific research of high quality. He used to argue that, well, I mean, if you have a 1-watt facility, then the only thing you can do is to bring a 100-watt mind to it. The more practical line which we might take in experimental research in India, considering what has been said, that we are in an era of sort of second quantum revolution, where the nature of quantum physics is being understood much more closely, and its consequences are likely to be very profound. I would say that one thing which we can try is look out for niche areas where there are possibilities. This is a shrinking and moving target, and the two examples I have mentioned here are topological materials. It turns out that there are about 1/4 or 23% actually of materials which have been surveyed in the last few years. They are topologically interesting. Now, of course, the most interesting topological materials have already been mined. But there is a catalog of topological phonon materials which was published, let us say, a few months ago, and a paper on there is a paper on topological materials discovery by large-scale indicators, which was published, let us say, 5 years ago. These contain a very large number of possible systems which may not need low temperatures, which will of course need very high quality crystal preparation and characterization techniques. But these are not that expensive. The other thing which I feel is very important is a spirit of Gandhian innovation. That is, an innovation which respects the high levels demanded of performance, but does it at an order of magnitude lower cost. This is possible. This has been done even in large institutions such as ISRO, which have shown that you can send things into space at maybe 1/5 the cost of what other countries require. The other most important thing, in my view, is respect for the natural world, not living in a world of denial. Resources exist for such an activity in this large, old, poor country, but I don't know whether we have what it takes. Thank you.
Thank you very much, TVR, not only for the knowledge. Topological phonons is new to me, but also thanks for constraining yourself to the time limit. Thank you. So if there are no brief comments, we will move over to Professor Grover, and we can always come back to ask questions to TVR. Professor Grover.
Thank you, Kia. Thank you, Kia. Can you hear me?
Yes, yes.
Okay. So let me share with you what I am currently doing at Punjab Engineering College, which is one of the oldest colleges in Chandigarh, and it's like the NITs, but it's not a part of the NIT system. So this is a college which attracts very good students, but which, before they invited me to be an honorary professor, had physicists embedded in an applied physics, applied sciences department. So after my joining, they trifurcated this department, and the physics department emerged as an independent entity, and the college wanted the enhancement of the role of physics in training
the technologists. So it is difficult to have the BTech students being loaded with more physics. So what the faculty at Tech thought was to institute an MTech program in quantum technology, taking advantage of the focus of the Government of India and the quantum mission. So we have thought of an MTech program in quantum materials in partnership with the leading national institutes, namely INST Mohali, IISA Mohali, IIT Roorkee, IIT Ropar, IIT Kanpur, and several other people from remote places have also joined this consortium to promote an MTech program in quantum materials for a period of 2 years, in which the students will get trained for a year at Chandigarh, but the second year they would spend with PIs which are located in different institutions. These PIs are mainly professional physicists who have advanced research labs. So the idea is to entice the students graduating out of the 4-year degree colleges with a physics honors degree, to tempt them to write the GATE examination and enroll into a MTech in quantum technology program, so that they get exposure to quantum technology related to this area, and also get experience in advanced investigations on materials preparation as well as measurement on materials. So this is an inter-institutional program which is in line with what has been taken up as a national mission. So I believe that such a program is built around what may be called as a laboratory-based research or small science-based research, which happens where a single individual with a niche lab can partner with other niche labs, so that the facilities are complementary, but the students who enroll for this program, they get exposure to a large number of complementary facilities by visiting these labs and having interaction with a large number of high quality co-PIs. So this program has some novel features, but it requires a novel kind of a support, so that the students and the PIs can travel to each other's institutions and come to. It's a kind of a hub and spokes model, which is embedded in a technology institution, but which is interfacing with a high quality physicists which are embedded in National Physics Institute. So if such a program is successful, I believe it can be replicated in other regions of the country, and we can really build a young human resource who will engage in the area of quantum technology, which is supposed to be area of much promise for the economic development. I don't know what I have said. I have able to convey you what we are trying to aim, but this is what we are trying to do, something new in our context. Thank you very much.
Thank you, Professor Grover. And I hope your hub and spoke model is taken up in earnest. But more than that, I hope that the small colleges, the teachers who are teaching them, are part of that spoke, because ever since the UGC minor projects have been stopped, I have so many of my girls who are teaching in colleges all around Punjab, Haryana, etc. They are not able to get any support for the small amount of research that they were doing. And to me, it is very important to keep up the research at that level, because they are the ones who are teaching our undergraduates.
So in this context, may I just add that on behalf of the science academies, few out-of-box recommendations have been made to the Anusandhan National Research Foundation. Have I lost the contact here?
No, I can hear you.
Okay.
We can hear you.
Okay.
Yeah.
Okay. So what we have said is that, a large number of our PhDs get employed in small postgraduate colleges and
Yes.
small universities, and they lose out as that age advances with the research. So we have made a very out of box recommendation that every academic in the country, in college, postgraduate colleges, small universities, they should be given 1 semester off after every 5 semesters of teaching. So they should be given a paid leave for 1 semester. And now that we have got used to guest lecturership, so the salary for the period that a researcher is on leave, paid leave, the substitute teacher's salary should be provided by the ANRF. So this way, and this should happen every 5 semesters. If we introduce such a scheme, then PhDs who are employed in undergraduate, in postgraduate colleges and small universities, they will be able to remain connected with the larger research group in some manner. So they will, if somebody takes a leave and doesn't deliver, he can cheat only once. If he wants to have this leave every 3, every 2.5 years, they will have to be productive and in both research as well as in some ideas. So I believe, and we are trying to ensure that these college teachers can also join the kind of the program that we are envisaging, and they can also participate in this national mission kind of a research.
Thank you. Thank you, Professor Grover. Thank you very much. And now I request Professor Bhaskaran to come and say a few words. Professor Bhaskaran.
Hello, Kia. Do you hear me?
Yes, yes.
Yes.
Wonderful. So thank you very much. And since already I have spoken for nearly 1 hour, maybe I wonder whether I can speak last after, or maybe let me complete. I leave it to you.
Okay. Don't worry at all. So we will go over to Professor S. Ramakrishnan, who has already given us a wonderful, view of the quantum scenario. So Professor S. Ramakrishnan, if you have.
Yeah, right.
Yeah.
Thank you. Thank you very much. I will be brief now since I have already said too many things. This is, as I said, I really emphasize that this is an era where, many things are happening, and not only from the physics side, but largely on the applications. And as you correctly said, we need to carry people along. People who are doing small research in the universities, teachers. Unless the teachers are trained, the students are not going to be trained anyway. So the within this view, the iHub, which I was a part of it, has 2 diploma courses already, short courses on quantum computing, and another one is on quantum communication. These are diploma courses, runs about, I think it's about 12 weeks or so. And then you got a certificate at the end of it. Apart from that, we have started the MSc in quantum technology. This is a course which is started from August this year. And already we had thousands of applications. We have about 30 students have been selected. They have going to finish the first semester. And we are now setting up a special lab for this. And because it is a quantum technology course, the labs are going to be like, real labs which are talking about quantum entanglements, experiments on, starting from the Stern-Gerlach experiment on the spins. How does one discover that? Plus, then all the new things about, 2-qubit entanglement experiments, 2-qubit quantum computers. And basically, this is a kind of lab where students are encouraged to try their own, when they understand, try their own things, both from the high end of electronics, because I think electronics as well as, the classical systems are the one which go into, which are there. which completes this quantum system. So we are looking at enabling technologies. If you look at, there are many people who are building in India quantum computers and communications and other things which are coming out of the quantum physics. But if you look at their classical subsystems, 99% are imported. I think cannot sustain for long. So what we are now doing, we had a workshop last year where I invited all the quantum specialists who are practicing uh, quantum technology to find out exactly what are the systems they need and how we can make these classical subsystems, at least to some extent, because the research has to go on two fronts. One is to build quantum computer network, quantum communication network, and so on and so forth. That is probably most of it, the imported classical systems are imported from abroad, but at the same time, some of the classical systems we need to make it here. So, I was totally a fundamental research scientist, and this exposure is extremely interesting to me, and it is extremely useful for the country. And as these big missions for centers are announced, I think they have a large role to play. The kind of support Grover has mentioned, it's very important that if 3 or 4 centers come together and talk about this program, and they should be nourished, and I hope that they will do that. And as I said, we need to expand from the few centers who are, of course, have the expertise to move on to at least engage the universities. It's not this kind of technology is not at the hands of simply physicists. The engineers have a large role to play. And I think unless there is a beautiful marriage of researchers and the engineers, and then of course the people who are marketing and so on would come in. So everybody has to work together to make this a success, and we should not miss this chance. I think we have missed many times. I mean, everybody has heard about the semiconductors where we lost out many things. This time I think people are eager, and we have actually, using the iHub Center, we have already sanctioned 12 startups, which are, companies which are going to make quantum technology products. And they are extremely interesting. And I hope, and we also supported nearly 100 scholarships. These are people who are working on quantum technology or these are fundamental research leading to quantum technology. We have supported their postdocs, undergraduates, and so on, more than 100 of them in the last 2.5 years of our existence. I think this is one way we must expand our activities to include all the universities, and that is the way to generate the manpower for this, to meet this revolution, which is really happening, and I hope it takes off the way it's supposed to do. Thank you. Sorry for a slightly longer talk.
Thank you very much. It was very illuminating. And I'm excited that there are so many new courses which are going around, because often the programmers ask me, how can we update ourselves with regard to quantum computing?
Yeah.
So
Yes.
you are a very good reference for that. Thank you.
So I would just send you this iHub website where we have a dynamic website where you can even ask questions, and how we can enroll these courses can be done. Okay.
Right. Wonderful. Thank you. And now I request Professor P.C. Deshmukh to please unmute yourself and start speaking. Professor Deshmukh.
Thank you. Thank you very much, Professor Kia. Thanks to IAPT for the opportunity to participate in this very eminent panel, which is here. And they have certainly proposed some great ideas. I would perhaps expand on some of these, which are not really new ideas. They have already been alluded to by earlier panelists. I'm thinking from the point of view of the platform where we are, which is the Indian Association of Physics Teachers. And we have, I believe, somewhere close to 10,000 members. Professor Aluwalia may correct me. We have about 10,000 members who are teaching in various colleges and universities across the country. I have been working with some small colleges and small universities, and I have opportunity to interact with some of these teachers. I'm enthused by this idea that, okay, you give them 1 semester off every 5 semesters, which was mentioned by Dr. Arun Grover. I'm, however, concerned that on a day-to-day basis, most of these teachers have so much of administrative load that getting a semester off after 5 semesters may not be very helpful, because they need to be in continuous touch, to some extent at least, with research on a regular day-to-day basis, not once in 3 years. I don't know what can be done about it, but perhaps some of the distinguished science bodies in the country can look into the matter and make specific recommendations to the University Grants Commission, All India Council of Technical Education, about the distribution of workload to teachers, because we are a huge country and there is enormous potential amongst the tens of thousands of students who are in the country. They are being mentored by these large number of teachers, and how we will generate, as Professor TVR said, that you need a high quality professional preparation, and this preparation has to be provided by the teachers to a large extent to their mentees, and this opportunity seems to be very limited in our education system. So I would think that to be able to do small science in an era of quantum revolution too, we need to intercept the present university, college education patterns, and perhaps all senior academicians who are involved in frontier research, if they can adopt like 10 colleges or 10 universities in the vicinity and at least once a month go and visit them, that may be one way of going forward. But I think a recommendation to the AICTE and the UGC about how workload should be distributed for teachers who can, I mean, it not only affects their opportunity to carry out research, however small, but it also comes in the way of their teaching, and they end up teaching in what does not always satisfy them. So these are some concerns which I thought I will share with you, but there are others who can perhaps throw further light on this and show the way to go forward. Thank you.
Thank you. Absolute ground realities. If anyone has a short comment on that.
Professor, can I have a perspective of the 2G IITs? I will take 2 minutes.
Okay.
Hello.
Just 2 minutes. Yeah, please
okay,
go ahead.
So like 2G IITs are relatively better endowed than university, but I would like to present a perspective from there, particularly the researchers who have been involved in research related to quantum techniques, whether at low temperatures or in other things like cold atom and so on. So, like we had a 7-year stay in Transit Campus, and that actually like led to drifting away of many a people because of lack of, like, we could not set up permanent facilities in Transit Campus. And then later on, the 6,000 crore budget is really a welcome that way that has come in. So, like on a personal note, like I have been smitten by superconductivity long ago, like during my PhD, and in these like 7 or 8 years where we were in Transit Campus, I worked on systems like Aurelius phase or in like carbon systems or resistive switching successively, where superconductivity was elusive, but we did get across relatively lesser known results on colossal Seebeck coefficient and Ovchinnikov ferromagnetism and so on. So, like, my suggestion was the following, that like these 30 hubs are really a great idea, like because we have about say about a 150 crore budget each, but about 10% of budget each should be dedicated to the following two separate points. One would be where about say 10% of budget should be put in instrument developments in individual labs spread across the country, where one does not really procure or buy a like commercial equipment or turnkey equipment, rather develop one. And another 10% should be spread out across maybe about 1,800 researchers across the country. Like a number I come to with a kind of point like about 7.5 lakh per year support, where they can do this small science and we can contribute. Like overall, we will get a mix of three good things: hubs, instrument
Dr. Thakur,
development,
sorry to
and
interrupt you,
yeah.
but please, can you conclude quickly?
Yeah, that is what is my conclusion. Yeah, here. Thank you.
Okay. Thank you very
Yeah,
much.
fine.
We have noted your very interesting points. And now I would request the last person on the panel, Dr. G. Bhaskaran, Professor Bhaskaran, last but not the least. Professor Bhaskaran.
Yeah. Professor Alwalia was raising the hand. So,
sir, you please continue, then I'll come later.
Okay, wonderful. Okay. So, you know, I'm a theorist, and already I spoke to you about my dream about room temperature superconductivity. So, from small science point of view, I have just two short suggestions. One is, you know, the silver gold nanostructures that our friends at IAC are doing. It's a very expensive way of doing nanostructures. However, copper is also a monovalent metal. I have already indicated it in my paper that whatever they do with silver, they could do with copper also. Now, it's amazing that back in 1940s or 30s, M.S. Rao at Annamalai University observed anomalous diamagnetism in cold work copper. It's a very well-known work. Japanese reproduced it, and then it went into the shelf. So I think then later it was taken up by others. People like Joe Imrie tried to develop a theory and concluded that it's definitely non-trivial and it needs understanding and explanation. In the wake of all these new phenomena of superconductivity and so on, it's worth going to back to some of these old works, which doesn't involve, it's a small science. You take copper, do some cold work, you get some small crystallites, then measure magnetism, and there is anomalous diamagnetism, which was already shown by Rao long back. He was Raman's student apparently. So just to reproduce and understand it in the modern context. Now, second thing I wanted to mention is that I wrote an article in honor of Professor Narendra Kumar when he reached 60. The title of my talk was that all basic phenomena in condensed matter physics mirror in biology. A hypothesis and few examples. So biology is laughing at us constantly. Nature is, if you look at nature, there are so many intriguing things, starting from photosynthesis, magnetotactic bacteria, and so on. So from small science point of, in fact, wherever I go, I tell my students and teachers whom I give lecture, please do some research on magnetotactic bacteria. It's a fascinating bacteria which lives in muddy, dark soil. Take the bacteria, it has about 20 monodomain magnets, which are like compasses built in its body. Only few people in California are working on it, and nobody is. I have been requesting my friends to dirty their hand and work on magnetotactic, because if you isolate that magnet, it's a monodomain quantum magnet. So already at the level of people who do a lot of nanomaterials and so on, worth understanding the physics from biology point of view. So I can enumerate many such things like photosynthesis. So small science, I think I cannot, it has to be, there should be some panel where many of these ideas are put together and made public to people to think about. So that's my humble suggestion. Like, again, exploring amorphous carbon in the context of superconductivity or liquid ammonia solution, metal ammonia solution. All these things should be tried, because just repeat whatever other friends have done 40, 50 years ago and see if by chance you see that, or in the process, with all our new developments and new understanding, maybe we can do better than them. Thank you very much.
Thank you. Very interesting indeed. Professor Ahluwalia, would you like to give some remarks?
Yes. Ma'am, please give me some time. I have to request you for that, because I think
over हो गया है, dinner miss
कोई
कर
बात
लो.
नहीं, हम 5-7 मिनट ऊपर नीचे कर लेंगे. Please,
ठीक है, ठीक.
I don't want to miss this opportunity to put forward.
Please. Yeah, that's true. Now that we are together.
Yeah. I am first of all very thankful that for the first time in the history of IAPT, let me put it like that, we had such a wonderful discussion and a kind of a inspirational program for our community. I am really beholden to Professor T.V. Ramakrishnan, with whom I was really talking, and he really made us do this. And I think after 3 days, we are very much enlightened about it. Now, because I am coming from IAPT and I am responsible for its activities, I would like to tell you a few things which we are very much interested in doing, and partner with the honorable members who were the speakers, who were on the panel, and who participated in this discussion. And that actually makes me feel that when this quantum revolution 2 is being talked about, what should be the role of IAPT as a kind of a conduit for taking this kind of an agenda to the stakeholders who are in schools, colleges, and teachers. Now, when I was talking about this small science, I really would agree fully with what Professor Bhaskaran has said. But can we really come together and create a kind of a list, curated list of the various small projects which can be done at the school level, college level, and the university level? I'm not excluding schools. Let me also tell you that in the last 1 year, 1.5 years, we tried to really become part of this quantum vehicle itself, that quantum, what you may call as the bandwagon which has started in the name of Quantum Revolution 2. And I hope you will be very happy to know that we did certain programs which we could not have even thought of. Like, for example, we did a program for almost 2 weeks on quantum computing for school teachers and students. And for that, the school's teachers came forward to take the responsibility to conduct that kind of a program. Now, only last month, we completed a series on physics education research. And the last lecture was very illuminating. That was given by a German professor, and she talked about what kind of curricula we need to bring in for encouraging students right from the schools to be ready for taking part in this quantum revolution to itself. And they have actually developed a curriculum which can be very easily implemented. Third thing which is there is this, that when the next year is coming, which is International Year of Quantum Science and Technologies, we did a small survey that after all, what is there which our community actually is looking forward to. And then, what we did was we listed certain topics in it or themes in it that in which kind of a theme you are actually interested to participate. Because for us, IAPT is like a big classroom. The way we really brought this distinguished, panel and the speakers, we can always, become part of that program in which we can sensitize and train people in a very big way. I don't know how we can get help from the kind of funding which is there for quantum, say, mission itself. There is another thing which is happening, and that is in the context of national education policy. National education policy envisages that we should have a 4-year degree program at the undergraduate level. 4th year is to be spent for the research. Now, if research is to be done at the 4th year level, what kind of a preparation our faculty has got? Can IAPT join hands in having some faculty development programs for those kinds of possibilities and opportunities which are waiting for us? I mean, that is my way of looking at it. And when I am talking about small science, I mean, can we really mentor those students who are coming at the 4th year level with certain very meaningful and exciting projects which Professor Bhaskaran has been talking about? Can we really give them those kinds of experiences, training, and work, maybe both in experiments and in theory, so that we find that the people who are coming from colleges or universities or PG departments, they are ready to take part in what Professor S. Ramakrishnan was talking about. I am looking forward to your suggestions on that. And I would like that the honorable panelists and the speakers, they become members of Indian Association of Physics Teachers, so that you may watch us that what we are doing and guide us and mentor our programs also, so that we become a very important part of this revolution which is taking place. Please believe me, we have very interesting networks which we have created. For example, we have a National Anveshika Network of India. We have a National Astronomy Network of India. Can I imagine that as a result of this 3-day program, we can think of a National Quantum Network of India under the banner of IAPT, where we can take up these kind of tasks. And we will be very happy that some kind of suggestions can come for undertaking this kind of a task and encourage a big number of people, which are around 10,000 as life members with us. So this is what I wanted to say. And I see, because I have worked in a college, I did my PhD when I was teaching in a college itself. I didn't go for any leave during that period. The problem was very tough. I talked about that in the lecture also. But I think it was very exciting to do all those things. Even when I just came out of my department, we had very interesting, FIST funding, which helped us to have a 128 core high performance computing facility. And we have worked on what Professor Bhaskaran was saying on graphene, on silicene, all these kinds of materials. And we got very good results. Molybdenum disulfide, for example. got very good citations also for those kinds of things which we did. I think there is a possibility, provided we also, start looking down on these kinds of, stakeholders which are waiting to participate in the quantum revolution. Thank you, ma'am, for giving me so much time.
Thank you so much.
I will welcome if there are any suggestions right now.
So to start, shall we start the cycle again? Professor TVR, would you like to say something? Would you like to add?
There is not much to add except that many of the things which have been said are possible. For instance, Dr. Ahluwalia himself referred to a program, a teaching program, a set of courses which can be constructed, which someone who gave a lecture in IAPT pointed out. It's also true that anyone who has an Android phone has access to almost all the information in the world. And if someone can actually make a list of what would be the best lectures in this field which are accessible, then that would be a very great thing. However, I also believe that in our enthusiasm, we should not forget the fact that high level of competence and training is absolutely essential. So this has to be monitored. The reason I also mentioned the two papers on topological matter is that there are hundreds or maybe thousands of compounds which are listed there as possibilities. These don't require very special and expensive facilities in order for them to be investigated. I had heard someone say that 90% of the discoveries, research discoveries in condensed matter physics are due to measurement of resistance. So if you measure resistance properly and understand what it means, you can figure out what is going on in many cases, and then devise the correct method of probing further. So we have a very large number of systems which we can study, out of which may emerge some new kind of quantum computing material. And that might be a complete breakthrough. What I do believe is that our desire to be a footnote to a footnote is what is going to keep us down. Thank you.
Thank you so much, TVR. I wonder if anybody else would like to add any small thing.
Yeah, so I just want to say a couple of words. I think for Professor Luvalia, you have touched upon an important point, and I think next year is going to be an important year because it has been, announced as the International Year for Quantum Technology. And IHub is a partner to this. And I think this idea was mooted when I was the IPA president. And IPA has a role to play in this as well. I think IPA along with APS projected this to the UN just a few years ago. And you have correctly said that, we need to make people aware of this quantum revolution. People have heard from lectures and so on, but nothing like demonstrating few things. And already APS has taken a stance, American Physical Society has taken a stance, and they have developed kits which can also bring the quantum revolution to the high school level. So there are kits available and so on. We are also thinking of developing such kits here at Pune and also procure these kits and so on. So this is something which we are planning to do, and maybe we could discuss with you exactly, the things which can crystallize between IAPT and iHub, and then we will take it forward, and then we could even apply to the National Quantum Mission to at least set up certain infrastructure which is required in this in this bringing this technology to the students and teachers, which is, I think, it's a very important thing. I'm sure the National Quantum Mission is also would welcome that. But at least we will do the framework, and I think I hope will help you to do this. Is that okay?
Yeah, I think this is a wonderful idea, and we will definitely seek you. I would put it like that.
Thank you. Thank you.
Thank you, sir. Professor Ahluwalia, if there is nobody else
Bhaskaran
ready
is waiting. Hello, excuse me. Bhaskaran has not talked.
I find that I have nothing to
He
say.
has, but
very
we don't
important
mind
things-
listening to him again.
Very important things have been said already. I'm just thinking about them. So at the moment, I have nothing to say. I'm just contemplating.
Thank you, Professor Bhaskaran.
PC देशमुख मैम
Ahluwalia ji, आप vote of thanks कर देंगे फिर?
मैम Professor PC Deshmukh, if he has something to say.
Professor Deshmukh, please. Please go ahead.
I already talked. I don't think I have anything further to add, but many good ideas have been presented by other panelists also. Very grateful to Professor Ramakrishnan, S. Ramakrishnan, for offering to work with IAPT. And as Professor Ahluwalia said, we will definitely use this opportunity. Thank you very much.
Thank you. Professor Ahluwalia from IAPT, would you like to
Yes,
say
ma'am.
the last?
Yeah,
Yep.
I think it has been a great privilege to be part of this program. I think we have really looked at a life from physics very, very closely. And I think there have been very many inspiring moments for each one of us, the participants. And IAPT is beholden to the honorable speakers, panelists, and the members who participated in it. One of the best things which happened was that on all the 3 days, whosoever came into the program, they never left. And that shows the success of this effort itself. And I must really thank Professor T.V. Ramakrishnan to make us do this. And we could do it on 13th of December. We started on the 13th of December, which was basically the last day of that birthday centenary of P.W. Anderson. I have to express my very sincere thanks to Professor Kuldeep Kumar, the President of Regional Council, Himachal Pradesh. We have in our country about 30 regional councils. We have a very good network of people with whom we really work around. And we had wonderful hosts in Sapna Sharma and Sapna Verma. And I think they conducted all the proceedings in a very, very dignified manner. I just would like to just make a request. We have a website, and I'm just trying to write down the address of the website in the chat box. Please visit our website and try to see that IAPT is in fact a happening place. And we are very much into those things which are needed by the country these days. I think we want to really be in touch with the best minds in the country, and that is what this program has done for us. I'm also thankful to my very worthy colleague, Professor Rekha Ghorpade. She has been there silently around. She was very busy in one of the programs. I'm very happy to tell you that IAPT had the responsibility of preparing students for International Junior Science Olympiad. we were given this as a full responsibility from HPCSC, and we have emerged as the country winner in that competition, and we have won 6 gold medals. Every team member of that actually did in an exemplary fashion. They were really wonderful. We also conduct a national standard examination every year. This year, 2 lakh students have sat in that. So what I want to say is this, that please have faith in IAPT. IAPT is able to do a lot of good things. It has the capability. We have been doing it for the last almost 40 years, thanks to our founders like Professor D.P. Khandelwal, Professor Babulal Saraf, Professor H.S. Hans, who really thought of this as a subject-based association. And I think that is where I must really thank each one of you to be part of this program. Thank you very much from IAPT and on my personal behalf.
Thank you. Thank you, sir. So with this, we come to the end of this program. So let me thank everybody and formal vote of thanks. So, sir, should I go for it?
Yeah, please.
Okay. So it's my privilege to deliver the vote of thanks at the conclusion of this wonderful 3-day webinar on the topic More is Different, Legacy of Nobel Laureate, on occasion of birth centenary of the great physicist P.W. Anderson. On behalf of the organizing committee of IAPT Regional Council, RC-23, Himachal Pradesh, I would like to express our sincere gratitude to everyone who made this event possible, and to all the participants who joined us for this celebration of science and intellect. A heartfelt thank you to our distinguished speakers, Professor T.V. Ramakrishnan, whose insightful talks on Anderson and modern condensed matter physics and Anderson's stance in physics not only enlightened us about the depth of P.W. Anderson's work, but also highlighted the continuing relevance of his contribution to condensed matter physics. A sincere thank you to Professor B. Bhaskaran, who beautifully connected Anderson's ideas to the broader landscape of modern scientific research, offering us a new perspective on the interdisciplinary nature of his impact. All of us enjoyed his 2 talks on secret of Anderson's success, and there is a room for room temperature superconductivity. Special thanks to Professor P.K. Ahluwalia for motivating us to organize this event and deliver a talk on More is Different, Legacy of our Nobel Laureate, which brought a deeper understanding of the work and life of Professor Anderson. We also had the pleasure of witnessing a thought-provoking panel discussion on opportunities for doing small science. The discussion was rich with ideas and suggestions and on how emerging scientists can pursue groundbreaking research on a smaller, more accessible scale, making science truly inclusive and innovative. I am certain that the conversation today will inspire many of us to explore new avenues in our own scientific journey. Our deepest thanks to Professor T.V. Ramakrishnan, Professor S. Ramakrishnan, Professor G. Bhaskaran, Professor Arun Grover, Professor P.C. Deshmukh, Professor P.K. Ahluwalia, and Professor Kia Dharamveer for taking the time to share their valuable knowledge and perspectives with us through this panel discussion. I would also like to extend my appreciation to the organizing team, especially the president of RC-23, Dr. Kuldeep Kumar, and everyone behind the scenes who worked tirelessly to ensure the smooth execution of this event. So finally, I would like to thank you all the participants for your active engagement throughout the webinar. Your comments and enthusiasm are what make this discussion and impactful. So thank you once again, and we look forward to your continued participation in future events. Good night, and thank you very much once again.
Thank you.
Thank you, sir. Thank you all.
Thank you.
Thank you.
Thank you, ma'am. Thank you.
Thank you, sir.
Thank you.
So thank you, Sapna.
Thank you, sir.
ठीक है चलो
So
Thank you all, friends. It was wonderful time that we had 3 days.
yes.
Remembering the
ठीक है
So thanks for everything.
नमकीन इधर इसकी बच्चा हाँ छोड़ नहीं क्या
Thank
होगा
you very much, sir. Thank you, ma'am,
लग रहा
for
है
this wonderful sessions
Thank you.
and wonderful webinar. Thank you, sir.
Thank you, sir. Thank you, everyone.
Thank you.